My name is Sophia Lemons. I'm an assistant professor of computer science at Earlham College in Richmond, Indiana, and I'm going to talk a bit about combating racial bias in machine learning algorithms. It's worth noting before we begin that, of course, I'm only one perspective on this, and in particular, I'm a white, queer, trans person with a background in artificial intelligence and education. I'll point you toward others who have different experiences and perspectives, and I'm always glad to hear from and be pointed myself toward others who could broaden my experience and perspective on things. So one of the common things that's stated and believed by many people about computing and computer science is that somehow computers are a neutral tool, and therefore any result that we get from a computer is neutral. It's all logical and has no background or bias or judgment of its own, and to some extent that is true. But understanding that computing is a human task and that computer algorithms and computers themselves are designed by humans and influenced by humans leaves us with, I hope, a little bit of a different perspective. And overall, this idea of neutrality is a very dangerous one. As Paulo Freire said, washing one's hands of the conflict between the powerful and the powerless means to side with the powerful, not to be neutral. And we see this play out in computing quite often. One big point to make is that what we actually do with computing and computer science really matters. We see examples time and again of either deliberate decisions by those in charge of developing computing algorithms or computing applications to enable harm and to allow for mistreatment of groups of people or things like that, such as aiding crackdowns on immigrants or helping to build AI for drones. And then we also see other cases where there's a more passive decision to allow things to be done with someone's technology, such as allowing things to be hosted on your platforms that, for instance, help to track women and stop them from leaving the country without permission of men in their lives, or creating a system for targeting job ads that allows options for illegal discrimination. And so these kinds of uses of computing are one pretty obvious way in which computing is not inherently neutral, because what people do with it really matters. There are often strong financial incentives for computer science applications to be created toward violence and oppression, as we saw in some of the examples before. These are all situations in which there's profit to be made in doing this kind of harm or allowing this kind of oppression to be continued. And there are often built into systems a lack of accountability for what's created, what's hosted, what's allowed, and what the results are from an algorithm making a decision or from an application that's being provided to the public. And if you look into incidents like the ones that were mentioned before, you will see those kinds of arguments promoted, and you will see that the companies can often get away from accountability because they have only created a supposedly neutral platform, but they've created one in which it's possible to do these kinds of things, and they haven't taken action to protect people who might be impacted by their software. So when we think about bias, there are many different algorithms that are created that help us to make decisions, to create new things, to speak to other people, and just in general, algorithms that do some thinking or some work for us. And these are very useful and very helpful. But those algorithms often have some amount of bias included in how they operate. Even aside from how someone intends to use the algorithm necessarily, there can be bias built into them. One of the commonly shown and sort of easiest to demonstrate examples is in automatic translation. Here we have an example of using Google Translate that we feed in the statements, he is beautiful and she is intelligent, and it's translated from English to Turkish. Now, what's worth noting is that Turkish is a language that, at least in these examples, does not build gender into the sentence the way that the English sentences had the gender he and she built into it. And when we go to ask the system to translate the Turkish versions back to English, it has to make some decisions for us. It has to make decisions because in English, we need an object with that, or a subject to that sentence, and the subject will typically have a gender associated with it. And so in this case, Google Translate chooses to translate these Turkish sentences without gender built into them into she is beautiful and he is smart. So it's made a decision there for us on what kinds of people might be beautiful and what kinds of people might be smart. It's worth noting that I had to redo this example relatively recently because Google did build in some tools to try to give back that choice to humans. If you translate only one of those sentences at a time, then you will get both options, she or he, no neutral options, but two binary options there at least. But when the text is longer, the algorithm is sort of forced to make a choice, or at least that's the implication, because it makes that choice for us, and it assigns gender in those two different sentences, and does so in this way that fits some systemic biases toward who's seen as beautiful and who's seen as smart. This is a relatively small example that still would have some impact on people, but these kinds of algorithms exist all around us all of the time. They're happening on your phone. They're happening in credit decisions that are made about people. They're happening in what's being promoted or suggested in advertisement all over the place. One other system in which these sorts of decisions are made is criminal justice systems. So this example that I'm showing here comes from a report by ProPublica on a software tool called Compass. It is a system that says that it is able to predict the likelihood of an individual re-offending if they're in the criminal system already. So if they have allegedly committed some crime, then information about them is fed into this tool, and it gives a rating, a risk of re-offending. And so here are two individuals, Dylan Fugit and Bernard Parker, who were assessed by the Compass system. They're just two examples out of many that were tested and that have been used. And this kind of system is actually used at times in bond hearings, in sentencing, in parole decisions, lots of different parts throughout the criminal justice system. It's worth noting that the tool does not explicitly include race as one of the features that it decides on. However, what was found was a bias with regard to race that rated non-white people, people of color, as higher risk with lower criminal histories, and when it was examined later down the line, with lower actual subsequent offenses. And so we can see in this example that though Dylan had a rating of 3, he had 1 attempted burglary as a prior offense listed, and subsequently went on to have 3 drug possession charges at later points after he was rated a risk of 3 by the system. Whereas Bernard had 1 resisting arrest without violence as his prior offense and had no subsequent offenses after being rated a 10 as of the time of the report that was given. And so we have to stop and think about, how does an algorithm like this, that does not explicitly include race or class or things like this in it, make decisions that come out biased? So, decision-making algorithms like these have to be given some model, some mathematical or computational model, telling them what is important, or some of them are allowed to build a model from a much wider range of possible choices. We could take an example of a hiring algorithm that helps human resource departments to do more decisions around hiring with less resources required toward it. For instance, trying to decide who are good candidates to bring in for in-person interviews, which can be expensive and take time. So an algorithm to make that kind of hiring decision might be given the components of an individual's resume, like the words that are used in there, the amount of time that they've worked at particular jobs, how many different places they've lived, who their references are, what the titles of their references are, what organizations they state they've belonged to. Lots of different things about the individual might be fed into the model. So the algorithm has to have some model to tell it what to pay attention to and what to ignore. So those kinds of features might be things that we encode and tell the algorithm, look at these. Look at what organizations they've belonged to, or how long they've worked at particular employers, or different job titles they've had, or things like that. Then those algorithms have to be trained using existing data to predict the likelihood of different correlations or outcomes. So going back to our hiring algorithm, it might look at all of those different features of the model, like duration at past jobs, titles at past jobs, titles of who their references are, organizations they've belonged to, and then it looks at things like, which of those past candidates that we've seen did we actually hire? And which ones were retained for X amount of years after hiring them? And we might consider these successful hiring candidates, and we might want to avoid the unsuccessful ones, people who we wouldn't have hired in the past, or people who we might have hired and who didn't stick around that long, and therefore we had to hire someone else and train a new person and so on. So the algorithms look at past data and see the relationships, the correlations between those features in the model and what was a successful outcome, what was the goal, the beneficial thing that we wanted. Then those decision-making algorithms optimize how they view those different features to best fit their predictions to the training data and the model. So they want to optimize to get the best matches, whether those matches are what kind of products a person might be most likely to buy, or who would be the best hire for this job that we're trying to hire for. So again, we can save money by only inviting people in for interviews who are likely to be successful hires according to that past data that the algorithm has examined and the model that we gave to it on what to pay attention to. So this can cause problems with bias being built into the algorithms. One of the reasons is because many of these algorithms are set up in a black box sort of way, meaning that the inner workings of them are hidden from people who might want to understand how the decision was made. So when it says these are the 5 people that you really ought to bring in for an interview, it's often difficult to understand why it selected those 5 people. And this makes sense when we view algorithms as property, as trade secrets and tools of a company that wants to make money off of marketing its product to different people, different companies, organizations, individuals. They want to conceal these trade secrets of how the algorithm makes its predictions because they don't want someone else building off of that idea and competing with them in the same market. Facebook, for example, has argued in court that they can't even reveal all of the types of data that they gather on users of Facebook, because even knowing the types of data that were gathered might give away some of their competitive advantage against other social media organizations, advertising organizations, etc. So not only how the algorithm makes the decision is hidden in that case, but even what data is being gathered and used in those decisions is being concealed in that way. And so this makes it difficult to see if we notice a trend in the kinds of decisions that are being made, whether that is actually being considered, whether that is a part of the model that's being used there. And often these algorithms are complex enough that even with some view into the inner working, judges, legislators, other non-computing professionals might not really be able to understand what is going on. Even sometimes computing professionals might not be able to understand all of the details of how the decision was made or how the different weights and values were assigned to those different pieces of the model. One other big problem that introduces and exacerbates bias in these sorts of algorithms is that the models often use proxies for what is the desired feature. For example, in the case of trying to see how likely a person is to enjoy a particular food product, we might use a proxy of how much of that food product people like them ate in the past. And these proxies are useful. We use them all of the time for making sorts of decisions, but they leave out important data. In that food example, how hungry people were in the particular setting that information was gathered, or how many alternatives they had. Was that product pretty much the only one that was around? Or how much was in stock of other competing products in that setting. So examples of proxies that are also used that you might have noticed out in the world in algorithms you've encountered is that popularity is often used for search results. When you're searching for something factual, what you're often getting back is something suggested based on its popularity. And this is how we can see things like fake news climb to the top of what should be factual reporting results for someone looking up information. What they get instead is a decision made on a proxy of popularity. And these sorts of proxies, as you can imagine, often stand in for something that we wouldn't have even wanted to be choosing on explicitly if we were considering it. For instance, the compass algorithm shown before that talks about risk of reoffending and was used in criminal procedures, it used features like the frequency that a person had encountered police and had been reported on in the past, their family situation, such as divorces or things like that, the amount of education that a person had had, the length of time that they had lived in particular places that they had lived, so how often they had moved, fights in school previously, lots of different features that were intended as proxies of other things related to how likely they were to commit a criminal offense. But many of those could be stand-ins for class, for race, for mistreatment that they might have encountered in the past, such as over-policing of the neighborhoods that they had lived in. So when prejudice is present in the existing data that's given to the algorithm, those algorithms often optimize to best match to it and fit it. Going back to our hiring example, if our past hiring practices led to only hiring a low percentage of people of color or a low percentage of women, then the algorithm will often notice that. It will notice it through proxies of types of organizations that someone belonged to, the Society for Women Engineers or the Society for Black Engineers or different things like that that might be present in the data indirectly. And so the algorithm will try to best match. If our hiring committees have themselves displayed bias, knowingly or unknowingly, that bias will be present in the data of who we hired in the past, and then will be amplified by the algorithm because it will try to optimize for it. It will say, a person like this is not likely to be hired. Don't spend the money on bringing them in for an in-person interview. And as we mentioned before with the black box component, it may not explicitly explain why and highlight for us the features that were used to make the decision of why to hire that person or not. And these sorts of things continue throughout the process. For example, if we look forward to the retention part, how long someone stayed with the company, if our office environment is unwelcoming, is a racist or sexist environment, then people feel unwelcome and they leave, and the algorithm will notice that and will also optimize to match to that and say that these candidates are not as likely to stick around and therefore fall lower on our ranking of who to bring in for interviews, which then creates feedback loops in which the algorithm sees the bias implicit in the data often and then fits to it more strongly, therefore not bringing in as many people of color or women or other categories of people that we would have had some amount of bias toward before. It will fit even more strongly to exclude those people. Then if new data is fed into the model to say, here are our new successful hires, then that set of successful hires will be even more biased toward whiteness, toward maleness, toward young people, toward whatever our previous bias had been when we fed the algorithm data. And one important thing to note is that often we lack access to data about real outcomes, other aspects of the situation, like an unwelcoming work environment, or the value of alternative decisions. We know in the example of the hiring algorithm, the retention of the people that we did hire and did keep, but we don't necessarily know the work history or the future work outcomes for the people that we didn't hire and didn't keep. It's very unlikely that our algorithm is going to be able to be given data on the people that we didn't hire after they went on to work somewhere else and perhaps were successful there. So we don't know what alternative models look like necessarily. We don't know what the other outcomes could be. In the example of something like the compass algorithm, if someone is given a harsher sentence and kept in prison for longer, then even if their data was fed into the system again later, we would see, supposedly, evidence of that system working, that that person who was unlikely to reoffend, hey, look at that. We put them in prison for longer and they didn't reoffend. That means supposedly that we made the correct decision here. So often, again, there are these feedback loops. This works similarly with over-policing. Algorithms can suggest to police where their patrols ought to be, and if they increase patrols in that area, they're more likely to witness crimes and to build longer criminal records for people who live in those neighborhoods, and it will continue as a feedback loop to reinforce the over-policing of that neighborhood, for example. And one last thing that bears mentioning about these problems with bias is that often companies who have this mentality that computing is neutral, and organizations and individuals who have this mentality that computing is somehow neutral and can give us neutral results, then take these approaches of ignoring race, ignoring gender, ignoring other avenues of bias, and saying simply, we didn't pay attention to those, and we don't want to pay attention to those. To pay attention to those would be the real racism or things like that, and therefore these kinds of bias go unnoticed and in fact outright ignored quite often. And it can take a lot of pressure to get companies to pay attention to these aspects of the people that are being impacted by their algorithms, like the example of Google making some alterations to their Translate software to give some more options on gender when the translation would be ambiguous. And this took many years of people pointing out this problem before it was addressed even at that level. One other thing about how bias can get into computing in particular is the aspect of who is allowed and encouraged to do computing, to do computer science, and who's sort of promoted as the faces of computing and computer science, and who's in the room when those different algorithms are being designed and those different decisions are being made. So it's important to acknowledge that in the history of computing and computer programming, women, people of color, women of color, had large roles in developing programming and computer science as a field. Here we have displayed from left to right Earlham's own Margaret Hamilton, Dorothy Vaughan, who you may have seen portrayed in Hidden Figures, Donald Cropper, K.C. Krishnan, Grace Hopper, and Norman Rothberg, all of whom were figures in, for example, programming and computing at NASA, in developing some of the early computers and computer programming languages in the case of Grace Hopper, and the women and people of color who played critical roles in the development of programming and computing. As computer science was professionalized, as it was formalized, brought into offices and universities, marketing for computer programming jobs switched from being targeted toward women and people of color toward being targeted to primarily white men and seen as this formal professional role. Women were, in many cases, pushed out or ignored in the history and culture of the field, and the icons that were promoted became primarily white men. And this leads to a present day in which there are near constant recurring problems of sexism and racism and other forms of discrimination and exclusion in actual computing companies, computer science departments of universities, research laboratories, etc. And here are just a few examples of Zillow and sexual harassment to extreme levels of female employees, Google attempting to cover up sexual misconduct allegations, and overall reports on toxic tech workplaces where harassment, stereotyping, and bullying happen and drive away women and people of color. So even if they are hired at a place, then often being pushed out in these ways. And costing large amounts of money, it's worth noting, and being very counterproductive on that side as well. To put some numbers to it, undergraduate degree rates in computer science or computer and information sciences, as it's sometimes labeled, from the NSF as recent as 2018 shows women earning about 19% of computer science or related degrees, Black or African American people earning about 9% of computer science or related degrees, with about 30% of those being women, and Latinx or Hispanic people earning about 11% of computer science or related degrees, with 18% of those being women. So we can see an overlap in the lower rates based on different axes of identity, of underrepresentation here. And this is an ongoing problem in computer science and in technology companies and computing as a field. So in that vein, what does an anti-racist, socially just, bias-combating computer science and computing look like? One of the ways that we can move toward anti-racist computing and computer science is accountability for the applications of computing and of computer science, holding companies accountable for the ways that they use computing and the applications that are created. So we've relatively recently seen Google employees speak out and act out about Google's collaboration on drone artificial intelligence. We've also seen that things were called to light about Facebook and ad discrimination, that they've created these systems in which someone can select to discriminate based on race or gender when posting, for instance, job ads, and that they were pushed to change that system. It's also worth noting that those discriminatory ads were discovered because Facebook was previously pushed to add information about why people were seeing particular ads. So they had to make their algorithm explain itself because people wanted to see why they were seeing particular ads or suggestions. And when they did, then it was noticed that discrimination was going on in those job ads. So accountability all around for applications of computer science and for how those are presented to us as well. Absolutely working toward an inclusive computer science culture and a welcoming computer science culture, an actively anti-racist, anti-sexist computing culture, anti-transphobic, anti-homophobic, etc., some place in which people are welcomed into the computing field and then are a part of the conversation and a part of the consideration when applications of CS are chosen and when the algorithms are designed and evaluated. So some examples of this are many computing organizations are adding codes of conduct for their communities, that if you want to participate in events or contribute to particular open source software, that you have to be a part of this inclusive culture and not a part of the exclusive cultures that have been historically built up and created around computing and computer science. And then other organizations like Girls Who Code or Black Girls Code or plenty of other organizations that devote resources toward bringing in communities that have previously been excluded and underrepresented in computing. And another way that we can work toward anti-racist computing is identifying bias, combating that bias, and demanding transparency from companies. One of the, I think, neatest ways that this is being done is the Algorithmic Justice League, which offers audit services to companies. They have put forward a pledge for companies to engage only in ethical behaviors in terms of some of the machine learning algorithms that are being developed and how they're being used. And IBM also, for example, has launched a tool for detecting bias in AI algorithms and explaining some of those automated systems. This is one step by a company toward trying to work in the opposite direction and be more explicit in looking for what kinds of bias might be in the model that an algorithm is using or in the data that an algorithm is being trained on. And there are conferences on fairness, accountability, transparency, explainable AI, and things like this to be able to encourage researchers and software developers to consider bias and racism and other things that might be a part of the work they're doing in ways that are often hidden from them or that they have not paid attention to in the past. How can you personally combat racism and bias in computing? Well, you can be aware of the applications that are being created or used by companies and organizations you interact with, like those projects by Google or projects by other tech companies to do harm to others, to allow discrimination, etc., and to speak up about those. Be a part of the ongoing movements or start a movement to combat some of those ways that computing is being used to oppress others or to do harm to others. You can advocate for the use of decision-making algorithms that explain themselves. You can say that I don't want the company I work for to be making HR decisions based on a box into which we've fed some information and out we get an answer that has no explanation to it and can't be engaged with or have any dialogue about it. And you can require information on how the designers of algorithms that you might use or that you might be affected by have accounted for bias. Have they done audits? Have they used a wide range of data sets to see if this algorithm exhibits bias toward particular groups of people? And you can work with organizations that are promoting inclusion in computer science and related fields to change the field of who's around and who's a part of doing that computing work, whether you do it yourself or not. And you can also recognize that your peers and colleagues from marginalized groups are likely already doing unacknowledged labor related to these issues. They are working against the bias that's shown by particular algorithms. They are often working with organizations that are trying to build inclusive communities. And you can join in and you can be a part of that work too. And if you'd like additional resources on how you can find this kind of bias in computing applications and algorithms, how these sorts of things got into the places that they have gotten into, and how they have actually impacted people, and what you can do about it, here are some additional resources. And thank you for the work that you're going to do to combat racism and build a more just computing world.